Hello, my name is Grant Steiner. I am a student of Civil Engineering Course 566, Earthquake Engineering, at the University of Idaho. Today I'm going to give a research presentation on liquefaction of gravelly soils. Engineers and geologists have long understood the impact of strong ground motion on the shear strength of soils. Through a phenomenon known as liquefaction, strong ground motion initiates increased pore water pressures, which in effect lowers the effective stress of the soils, resulting in a net loss of shear strength and the soil behaving as a liquid. This action can cause intense ground deformation and settlement, leading to massive infrastructure damage. Liquefaction will not occur for just any soil. There are very specific conditions during which soil will liquefy. In general, the soil must be saturated. Undrained conditions must be present to prevent excess pore water pressure from dissipating rapidly. The soil must be of relatively loose, soft consistency, and there must be a large enough ground motion or acceleration to trigger liquefaction. Typically, liquefaction is observed in sands and silty sand soil. However, it has been observed in both fine-grained soils as well as coarse, grainy materials composed mainly of gravel. As stated in the previous slide, liquefaction is typically observed in sandy soils. In fact, until the early 80s, the chief belief was that liquefaction was only observed in sands, and that gravelly soil would not liquefy. However, through the field observations of past earthquake events, laboratory investigations, and examinations of the geologic record, we have learned that gravelly soils not only can liquefy, but they have liquefied in the past and have been responsible for widespread infrastructural damage. Much like sandy soils, gravelly soils will only liquefy under certain conditions, and the liquefaction resistance of the soil is controlled by several parameters. Some of the more important parameters controlling liquefaction resistance of gravel are relative density, particle size and gradation, condition strength of individual soil class, and stratigraphic position. Studies like Kukosho 2004 and Zanaki 2007 performed cyclic triaxial shear tests on identically graded and composed soils at different relative densities to assess the effect of relative densities on the liquefaction resistance of gravelly soils. Both studies found that liquefaction resistance was highly dependent on relative density, and in fact, relative density showed greater control than gradation, percent gravel, or class condition. As one might expect, the correlation observed was that as relative density increased, liquefaction increased. Kukosho 2004 performed a series of cyclic triaxial shear tests on gravelly soil specimens at the same relative density but varying uniformity coefficients. They found that as the uniformity coefficient increased, the soil becomes more well-graded, liquefaction resistance increased. Evans and Zhao in 1995 performed a series of cyclic triaxial shear tests on specimens at the same relative density but at varying percentages of gravel particles. They performed tests at 0, 20, 40, 60, 80, and 100% gravel. The study found that as gravel percentage increased, liquefaction resistance increased. They found that a sample at 40% relative density with 40% gravel performed similarly to a sandy soil at 65% relative density with no gravel particles. Kai Hua Tan in 2004 performed a series of triaxial shear tests on specimens at the same relative density and at the same percentage of gravel, but with varying sizes of gravel particles. This study found that as the size of gravel increased, the liquefaction resistance increased. A soil with 1-inch gravel particles was found to have 2 to 3 times the liquefaction resistance of a soil with a gravel particle of 1/2 inch. Kukosho in 2004 performed a series of cyclic triaxial shear tests on soils with the same relative density and same gradation but with different strengths of individual class. One set of tests was performed on soils composed of alluvial gravels whose gravels were relatively hard and unweathered. The second set of tests were performed on soils composed of fragments of decomposed granite. The class for these gravels are highly weathered, decomposed, and relatively friable. The study found that the alluvial hard gravels had a much higher liquefaction resistance than decomposed gravel samples. Gravels, by their coarse-grained nature and depositional environment, are typically highly permeable and thus able to rapidly dissipate pore water pressure changes. As noted earlier, one of the fundamental conditions for liquefaction to occur is a soil must have undrained conditions, or be unable to dissipate pore water pressure changes rapidly. The highly permeable natures of gravels can be overcome if certain stratigraphic conditions are present. Some of these conditions are gravel layers encapsulated by less permeable soil. It should be noted here that less permeable does not mean impermeable. Encapsulating soils just need to be less permeable than the gravel so that they impede dissipation of pore water pressure. Another condition is the presence of interbedded less permeable layers of soil. An additional condition is if there is an appreciable amount of fines and less permeable soils in the voids of the gravel, which will impair drainage and dissipation of pore water pressure. Finally, liquefaction of gravels can occur if the lateral and vertical extent of the gravelly soils are large enough that pore water pressures cannot be dissipated rapidly. While examples of liquefaction of gravelly soils are not as exhaustive as are those for sandy soils, liquefaction of gravelly soils have been observed in the field in several historic earthquakes around the world. During these earthquakes, liquefaction of gravelly soils caused widespread infrastructural damage and loss of human life. In the following slides, I will detail a few of the more significant examples. On June 28, 1948, an estimated 7.2 earthquake struck Fukui, Japan. Fukui had been constructed upon an alluvial plain consisting of relatively loose silt, sands, and gravels. Groundwater conditions on the alluvial plain were extremely shallow, in many cases less than a meter below the ground surface. The duration of the ground motion was about 40 seconds, and the damage that ensued was quite remarkable. Over 75% of the structures were completely destroyed, and about 5,000 people were killed. The majority of the destruction was caused by liquefaction, and fires caused by the structural damage from the liquefaction. In the areas where gravel underlay the city, the gravel was capped by about a 1 meter thick layer of clay or silty clay topsoil and was underlain by sandy salt or silty sand. These bounding layers are likely to have created hydrologic confining conditions for the gravel layer when the intense seismic shaking occurred and pore water pressures skyrocketed. On March 27, 1964, an estimated 9.2 earthquake struck near the Prince William Sound in Alaska. This earthquake triggered widespread destruction across Alaska. At the town of Valdez, liquefaction of gravel was observed. The town was constructed upon the floodplain and glacial outwash of the Valdez Glacier on the coast of the Pacific Ocean. This glacial outwash consisted of unconsolidated, saturated, loose sand, silt, and gravels. The earthquake triggered unprecedented liquefaction, causing huge lateral spreading, leading to approximately 100 million cubic yards of soil sloughing into the ocean beneath the ocean surface. This huge displacement created a 30-foot-high tsunami that completely wiped Valdez out of existence. On October 28, 1983, an estimated 7.2 earthquake struck central Idaho, about 20 miles northwest of McKay. The areas affected were the Lost River and Thousand Springs valleys. Both valleys consisted of loose, Holocene alluvial sediments consisting mostly of sand, gravels, and silty gravels. Groundwater in the valleys was very shallow, and upon initiation of the seismic event, liquefaction quickly ensued. Large ground surface displacements were observed that were a result of lateral spreading occurring from the liquefaction of the underlying 6 to 12 feet of gravel sediment. Widespread structural damage occurred in the Bay, Idaho. However,